What will I learn in 207? We're going to start with a discussion of waves, simple harmonic motion and waves. And that will include a discussion of music. And we'll find out that Greg doesn't know very much about music. Then we're going to turn our attention to electric fields and electric forces. There I am, holding a Van de Graaff generator. Yeah. The head's not me, but the rest of it is. Yeah, just they make good food in Mexico. I really like their food. This turns out to be one of the more challenging parts of the class, and it's because the electric field is invisible. Now, we've encountered a field before. Technically, we didn't really talk about it much that way. But we encountered the gravitational field. And we said that the gravitational field was 9.8, we're going to call it 10 newtons for every kilogram. So that field strength told us how much the Earth pulled on every 1 kilogram of mass. Now, if I were to try to visualize that gravitational field, every point in this room would have a vector associated with it. That vector would point straight down, and all the vectors would be the same length. 9.8, call it 10 newtons for each kilogram. And that's pretty boring. Now, the electric field is just so much more robust and interesting. If this water bottle was a positive charge and these glasses were a negative charge, that would set up an electric field in this room that was everywhere different. Over here it might be pointing this way, and over here it might be pointing that way. And in some places the vector would be long, and some places it would be short. And if we had special glasses that could visualize these vectors, it'd be bizarre. It would be a mess. The whole room would be filled with different length vectors pointing different directions. And so what we have to do is figure out a way to visualize that without going stark raving mad. And that's why we use field lines, electric field lines. So we'll talk about and use electric field lines. The third part of the course is my favorite by far. This is what I live for, is teaching the electric circuits. During the summer, I bring high school teachers and junior high school teachers from all around the country and teach them electric circuits. This is fun. And we're going to do it in a way that's different from the way it's done everywhere else. Pretty much everywhere else. Okay? We're going to build a conceptual model that will actually explain what's going on in these circuits. If these 7 bulbs are all identical, and by that I mean they were made on the same day by the same worker in the same factory, and I hook them up to a battery in this orientation, and I ask you, which is the brightest bulb, which is the second brightest bulb, which is the third brightest bulb? Actually, that's going to be one of your homework problems, that right there. And you're going to be able to say, well, Greg, bulb 1's going to be the brightest, bulb 7's going to be the second brightest, 6 will be third, these 2 will be tied for next, and 4 and 5 will be tied for last. And more than that, it'll just make sense. You'll be able to justify your answer. You'll be able to prove it. Not with equations, but with ideas. Okay? You'll also be able to do the equations because everyone, the MCAT expects you to do that. But if you learn those equations after you have the ideas, you understand it at a deeper level. Okay. Now, we save magnetic fields and forces for the end of the semester. Now think back a moment on 205. We did linear motion and linear dynamics, linear forces. And then we talked about energy and momentum and buoyancy and all these things. And then right at the end of the semester, we came back and we did rotational motion and rotational dynamics, torque. Why did we save that for the end of the semester? Why not just do it when we were doing the linear stuff? And the answer is, it was hard. And it was hard because it was weird. You remember that when we had a spinning wheel, when we tried to push it one way, it always went a different way. It always went 90 degrees to the way we pushed it. And that meant we had to use something called a right-hand rule. And there was a whole lot of goofiness involved in rotation. And that's why we saved it for the end of 205, is because you weren't ready. You weren't ready for the truth, okay? Now, we saved magnetic fields for the end of the semester for the same reason. We're going to find that when it comes to the magnetic field, everything gets pushed exactly 90 degrees to the direction you think it should be pushed. And there's not one right-hand rule, there's 3 right-hand rules that you have to learn how to use. And so because of that goofiness, we save it to the end when you're ready. Okay, but it's a fun topic. There's a lot of really fun things you can do with the magnetic fields and forces. Now, let's get started. We're going to start with a review. This is 205. This is not new stuff. This is 205. You've been here. I put a spring on that support, and I take a 500 gram mass, half a kilogram. Now, without the mass, the bottom of that spring is right about 10 centimeters on this scale. When I put this mass on here, it stretches the spring. Now the bottom of the spring is right at, it's about 22 centimeters. So it stretches at 12 centimeters. So that means that the mass is 500 grams. Remember, when we have grams, we always put that in kilograms. And the stretch, we call that delta S. Okay? That delta S is 12 centimeters. But remember, we always have to convert everything to meters. So that's going to be 0.12 meters. Now, folks, again, this is 205. What's the spring constant of that spring? This is not new stuff, old stuff. With your neighbor. You just met your neighbor. Talk to them. Okay, time to rat out your neighbor. How many of you are sitting next to someone who forgot over the holidays? Yeah, okay. Remember, we had this little thing called, what we're going to do is we're going to put that mass on, we're going to let it stretch to a new equilibrium position. There's the stretch, delta S. We're going to use something called Hooke's law. Remember? Hook. And Hooke just tells us, Robert Hooke just tells us, that the force exerted by a spring is proportional to how much you stretch the spring. You stretch it twice as far, it pulls back twice as hard. And the constant of proportionality is that spring constant K. Now there's that minus sign there that talks about direction. If you displace the spring down, the spring pulls up. Those are in opposite directions. But we typically ignore that minus sign because it really just, it tells you something obvious and it confuses when you try to use it to get answers. So usually we're just going to ignore that minus sign and use our gut to get directions. Now, let's use that to solve this problem. I have this spring, it's that long. When I put a mass on it, it stretches out. Let's call that the block. And it stretches that spring by an amount delta S. And it has mass M. Now, if I draw a free body diagram for that block, A free body diagram. That is so 205. Yeah. Turns out we're going to be doing free body diagrams over and over and over again in 207. There's going to be so much of 205 that's just going to be useful in 207. You're going to wish you paid attention. Okay? Now, the first force we put on any free body diagram is the gravitational force, the weight, the earth pulling on the block. And remember, that's just the mass times the gravitational field strength. That's going to be half a kilogram, and the field strength is 9.8, let's call it 10 newtons for each kilogram. And that's going to give me 5 newtons. Sorry, misspelled N. I then ask, are there any magnets in this problem? No. So what touches the block? The spring. Does it push or does it pull? Yeah. That's the thing about springs. Sometimes they're pushing and sometimes they're pulling. When they're stretched, they pull. When they're compressed, they push. And so rather than switch back and forth between normal and tension, we're just going to label these as a capital F by the spring. And I know that if that block's just sitting there with no acceleration, that the net force must be 0. So that means that this has to also be 5 newtons. Remember, this is the most important equation that we had in 205. And the way we read it is a net force causes a mass to accelerate. Okay? Now, if I go up here to Hooke's law, and I plug in 5 newtons, and I plug in 0.12 meters, and I forget about the minus sign because that just gives me direction. I'm just looking for the size of K. K is always going to be a positive number. That's going to give me a K value of 5 newtons divided by 0.12 meters, and that's going to be 41 newtons per meter. Okay? Now again, that's 205. That's a review. That's not what we're about here. In 207, we're doing this. A mass bobbing up and down on a spring. And we call that simple harmonic motion. The most important word there is simple. And I'll explain to you in a little bit why it's simple. Now we can characterize simple harmonic motion by the timing of the motion. We can do that 2 ways. We can either talk about the period, the time it takes to make one oscillation, one down and back up, or we can talk about the frequency, how many times it makes oscillations per unit of time, per second. Okay? This motion in terms of the amplitude. And we define the amplitude as the furthest distance that this thing gets away from equilibrium. How far does it get away from its happy spot, where it would just rest forever and not move? Can I just pause a moment and ask, how many of you right now deeply care about masses bobbing on a spring? That's just something you've always been dying to know about? You'll notice that my hand's not up either. Okay? No one in the room cares about masses on springs bobbing up and down. So why am I forcing you to learn about them? Well, it turns out that if you put on your magic glasses that can see microscopically, things that seem solid really are made up of a lattice work. And if you look at that lattice work, it behaves very, very much like masses representing the atoms and molecules in a lattice with their neighbors, connected by forces that can be represented by the springs. These forces happen to be electrical, but in practice, it looks like a whole bunch of masses connected by a whole bunch of springs. And so it turns out that if you understand this problem, you understand the world around you. Now, I did not fully understand that concept. I did not fully appreciate it until I got to MIT. Now, MIT accepts graduate students from all over the world. Every country in the world sends their geekiest people to MIT. And all of those different places have different grading systems. And so they're not really sure that everyone belongs there. And so the first thing you do when you get off the bus is you take a 5-hour qualifying exam. And that qualifying exam is to see whether you really belong there or whether you need to get back on the bus and go home. Now, I knew in my heart of hearts that I didn't belong there. I knew that everyone there was smarter than me. I knew I was going to fail this exam and get back on the bus. When they gave me the exam, the first question on the exam was this motor, a heavy motor that was turning. The motor was sitting on a thick rubber mat. And as you changed the rotation speed, you found a particular speed at which this motor bounced up and down at the largest amplitude. Now that was it. At that point I just panicked. I had never in my undergraduate studies encountered a problem anywhere remotely similar to that. And I knew I was going home. And I sat there and I just stared at that problem for the longest time, wondering how I would tell my wife that we were packing again. And then I realized that the motor was going up and down, up and down, up and down. Simple harmonic motion. I realized that the mass of the motor was the same as the mass of this block. And the rubber pad, the rubber mat, was acting like the spring. And they gave me enough information about the mat to figure out the spring constant of the spring. And suddenly, it became a mass on a spring. And I solved that problem and I turned the page, and dang if it wasn't another mass on a spring problem just dressed up as something else. I kept solving that same stupid problem over and over again, and I got to stay at MIT, and that's why I have the job I have today. You may not care about this problem, but I think it's the most important problem in the world. It allows me to teach you. It allows me to come and work with you. Okay, let's start simple. You got a block on a spring that bounces up and down every 0.25 seconds. How many times can it bounce up and down in 1 second? It's not rocket science. 4. Yeah, all you did is take 1 over 0.25. Okay, if the period is 0.25 seconds, you can fit 4 of those into a second. Okay, so the frequency is 4 oscillations per second, and we give that the name Hertz. HZ. That's just to honor a dead professor. The most noble thing you can do with your life. Okay? Now, you can see that the period is just the inverse or the reciprocal of the frequency and vice versa. That the frequency is 1 over the period and the period is 1 over the frequency. Okay? So if you know one, you know the other. Now, this is an old exam question, a simple question. We're going to use our clicker to answer it. What is the frequency of the second hand on a clock? And we're assuming an analog clock, not a digital clock. Okay, and folks, if you didn't bring your clicker today, that's fine. I'm not going to collect clicker points for credit until next Wednesday, so don't panic. And you can register your clicker I should have told you this earlier. You can register your clicker on the very front of the D2L site. There's a little link that you can click and go do it. As long as you do that before the last day of class, you'll get all of your clicker points for the semester. They'll come raining down on your head. Okay, so let's see how we did. D is the correct answer. Good job, people. Okay. The frequency is just number of cycles or repetitions per second. Well, a second hand goes around every minute, every 60 seconds. And so if I want to know how many cycles happen in a second, I divide 60 into 1, and I get 1/60th of a hertz. Okay? Now, what if I want to change the period of the motion? What if I want to increase the period? I'm going to keep the same spring, but I'm going to change the mass. Should I reach for a smaller mass or a bigger mass to increase the period? Talk to your neighbor. Which would it be? Which of those? Okay. Think about what I'm asking. If I increase the period, am I making this thing move faster or slower? Shout it out. Slower. So to make it move slower, I'm going to want the larger mass because it's harder to speed up and slow down. It has more inertia. Whoa, whoa, whoa. Like trying to move a football player. Okay? If I put a smaller mass on there, okay. Now, what if I had asked you what you want to do if you want to increase the frequency? Am I making it move faster or slower now? Faster. So I would decrease the mass. Decrease the mass. Okay, now this is a very, very simple exercise just to make sure that we're all on the same page. There's two flavors of this problem. There's the problem where the mass bounces up and down on a spring. There's the easier situation where it bounces left and right. Now folks, when we do these problems, we have to slide on something. And we're always, always, always in this class going to slide on the frictionless table. Where do we get those frictionless tables? In the basement of the physics building. Okay? Now, if you put friction into this problem, it becomes a very rich problem, a very important problem for everyday life. We deal with this problem in the Physics 301 class that's taken by our physics majors. You solve it with a differential equation. It's a very fun problem. But in our case, we're always going to take the frictionless table, and so this block, it's just going to bounce back and forth, back and forth, back and forth between this turning point and this turning point. I've shown you the positions where it stopped to turn around and go the other way. Now, with your clicker, tell me what the amplitude is. Okay. Last call. If we all get this right, I take you all to Mexico. Okay. The most common answer is B, which is 0.5 meters. That is not the correct answer. That is not the correct answer. You remember, we defined amplitude as the biggest distance, the greatest distance it gets away from equilibrium. Well, what's equilibrium? Equilibrium is where the forces are balanced. In this case, the weight force is always going to be balanced by the normal force by the floor, the table. So we're looking for a place where that force by the spring is zero. Well, when the spring is compressed, it's pushing to your right. When the spring is stretched, it's pulling to your left. The only place where the spring is neither pushing nor pulling is right in the middle, between the two turning points. At that point, the spring is just exactly the length it was when it came out of the box from the factory. Okay? Now, the biggest distance it gets away from that equilibrium point is 0.25 meters, and that's the amplitude, is 0.25 meters. So very few of us got that right. Okay? And I'm not going to take those few to Mexico because that'd be expensive. Okay. Now, you've got a block hanging from a spring. It's pulled down 10 centimeters and released. It bounces up and down at a rate of 3 times per second, 3 hertz. You want that rate to be increased, maybe to 4 hertz. Which of these things in the list, or maybe something else that you can think of, could you do to make that happen? Talk to your neighbor. Which of these things would increase the frequency?
So increase the frequency, decrease the mass?
Yeah, that's what I was thinking, make it very fast.
Yep. How about push it faster?
You could, I was thinking also you could make the string stiffer so that way it's got less momentum.
Okay, brave soul, where are you? Raise your hand. Which would you do?
I picked 3.
Which 3?
Increase the mass, make the spring stiffer, and not pull it down as far.
And not pull it down as far. So you'd pick this one, and this one.
Yes.
Okay? Anyone have a different answer? Yes, sir.
I would take the pulling it down farther out of that list.
So you think it's only 2 things?
Yeah.
Okay. Let's test that out. You both agree on these 2, right? Decrease the mass and make the spring stiffer. Let's see about pulling it down further or less far. If I pull it down a little bit, boing, boing, 1, 2, 3, 4, 5, 6, 7, 8. Okay? Now if I pull it down further, 1, 2, 3, 4, 5, 6, 7. It's the same rate. That's the simple in simple harmonic motion. Simple harmonic motion will never, and by that I mean never, depend on the amplitude. Never. Ever. Now why? I don't know. That's just the way the world works. We have no right to expect that. It simplifies the mathematics immensely. It also gives us a lot of rich behavior that has caused bridges to fall down, called resonance. Okay? And that principle is that simple harmonic motion of an oscillator only depends on 2 things. It depends on how stiff the spring is, or whatever restoring force you have in the problem. Whatever's acting like a spring. And it depends on how hard it is to move the system, how much inertia there is in the system. In this case, the mass of the block. Now, it's always independent of the starting conditions and the amplitude of the motion. In other words, it doesn't matter whether I pull it down and release it from rest, 1, 2, 3, 4, or whether I start it by hitting it. 1, 2, 3, 4. I get the same frequency regardless. Now we can do a lot of fancy math and derive this formula, but it's going to take a lot of time. Instead, let me just give you the result. The period depends on the mass of the block and the spring constant of the spring in this way. And since we know that the frequency is just 1 over the period, we also have this formula. And those will be on the front page of your midterm. Now, this gives us another way of determining a spring constant. We found the spring constant of this spring, we found it to be 41 newtons per meter by using the 205 approach. We hung the mass on the spring, we let it hang there, and it wasn't moving. We call this the static approach for finding K. There's another way of finding K. We know that the period of oscillation is 2 pi times the square root of the mass over K. So if I know how long it takes for this to go up and down, I know T. If I know the mass, I know M, and that means I can use this equation to find K. Well, let's simplify this equation so that we can find K more easily. If I get this out of the square root by squaring both sides, and then I get the K out of the basement by cross multiplying, I have a formula for K. Now let's use that to find the spring constant for this same spring that we used at the beginning of class. I'm going to take the half kilogram, and we're going to time how many seconds it takes to go up and down 10 times. Who's got a stopwatch on their phone or wrist? Or come on, somebody help me out. You got it? Okay, Tori, I'm going to tell you when to start and when to stop. Ready, begin. 1, 2, 3, 4, 5, 6, 7, 8, 9, stop.
7.2.
7.2, okay. So 7.2, is that the period? That's how long it took for 10 oscillations. So that means the period is going to be not 7.2, but 0.72 seconds. So if I go down here and solve for K, 4 is equal to 4. This is a little trick that you learn when you do a lot of problems. Pi squared is about 10. And M is a half a kilogram. And the time, the period, is 0.72. And that's squared. Now, 4 times 10 is 40. That's multiplied by 0.5 is 20 over 0.72 squared. And that equals 441. What is it really?
You're good. We'll just discuss it.
He's got it, he's got it, he's got it. Don't choke. Oh, you're not doing it. He's texting his girlfriend.
Yeah, simple calculator, difficult to work with.
Okay, we're going to say that's 41, because that's what I want it to be. I want it to be that really bad. Okay, folks, we've run out of time. Welcome back to physics. We're going to have fun. I promise.